The ability to transform functions is invaluable when it comes to looking at applications. It's incredibly rare outside of pure mathematics to encounter a quadratic y equals x squared in any but the simplest possible models. It's much more common to have some transformed version of them to bring them into the scale of your problem. For example, let's consider some data, and we've gathered some data and it seems to describe a slowly growing function here. And one of our tasks along the way would be to decide if we can represent this data by a formula, by a function. And how would we go about doing that? Well, the first thing we should do is look at our catalog. This is almost a design question. What do we have in our toolbox that can be made to fit this particular shape? And there's some things that we notice right off the bat. It seems to have some kind of horizontal asymptote here. And if that's the case, that's an important feature because it really limits our choices for the functions that we can use. One of the examples we might consider is trying to fit a polynomial to that, but right off the bat we know that that's not going to work. Let's emphasize that with a big red X. That's not going to work because all polynomials keep growing without bound. If you look at quadratics, they grow, cubics, they grow, fourth orders, however you construct them, they keep growing and growing and growing at both ends. There's no way to turn a polynomial into this kind of shape. There's just no way for that to happen. Other things we might consider would be sine, of course, and cos, but those don't make a lot of sense either. There's no oscillations, no periodicity here. So those don't fit at all. None of the trig family really belong. No periods. So then what does that bring us to? Well, okay, polynomials, rational functions might work, but they seem pretty complicated. We'd like to start simpler if we could. So what are the other things? Logarithms, again, no asymptote, so they would be out. Let me emphasize here, no horizontal asymptote. They do have a vertical asymptote, of course, but out of the big four, that would leave exponentials. And they, fortunately, do have a horizontal asymptote. Remember, if we draw an exponential curve, it looks like that, but there is a horizontal asymptote in them. Well, that gives us some hope. Now, of course, this shape here is not the shape of the natural exponential graph, but maybe we can make it all work if we transform it correctly. So, let's take a look. Let's see if we can generate a mathematical form for this function based on this graph. Well, let's start off with our exponential. Now, the first thing we recognize is that we want the graph to fade to the right. We want the asymptote to be on the right-hand side, not the left. So if we think of the graphs that we know about exponentials, that's e to the kt. But if we put a negative value in, let's keep our colors consistent here. If I want to something to have an exponential horizontal asymptote on the right-hand side as t increases, then that can be obtained by having e to the negative kt. So that would already give us this shape. But then we'd like to have it flipped upside down. Well, if that's the case, we're going to have negative something, e to the negative kt, and we're probably going to want it scaled as well. We don't want this gap here to always be 1. So we're going to need some kind of constant out front. Let's put that in here. And we notice that if we were to draw that function as it is right now, we would have the asymptote coming up towards y equals 0, but we need the graph to be up at 15, so we're going to have some shift on top of that. So gradually we can build together some template, essentially, for an exponential function that would have this shape, and this would be its formula. We can confirm some of that formula and that it'll work by identifying some of the particular values. So one of the things is that the horizontal asymptote is out at 15 at y equals 15, or concentration equals 15. So that means that instead of having our graph converge towards 0, it needs to be shifted up so that it converges towards y equals 15. Well, how are we going to do that? We're going to need a 15 out front. All right. The negative sign we already had for flipping this vertically to get the the inverted or flipped exponential graph. And what else can we figure out? Actually, we can figure out another ingredient here, which is when if our graph goes through the point 50 here, then this gap is now 10. On an ordinary exponential graph, that gap would be 1. So we're going to need to scale this up. This gap here has to be scaled by a factor of 10. So immediately we can put that 10 scaling factor in front here. That's probably about all we can do at this point. The last variable we haven't determined, actually it's a parameter, it's a number that would be fixed. We'll get to talk about that later in the course. But that k value is about how quickly the curve decays. And we really can't tell that without a bit more information. Let's go to the next slide. Okay, here we can pick out maybe one point, one representative point. After 30 hours, we get to 12 parts per million. Okay, so if our C of t formula was 15 minus 10 e to the minus kt, and we have the point that we know now as 3012, but this is t and this is concentration at that time. Now we have a point that we can use with our formula to solve for k. Let's do that. So t equals 30 and c at that point is equal to 12. Gives us the relationship that 12 equals 15 minus 10 e to the minus k times 30. Alrighty, that leaves us with only one variable left to solve for, the k, and we can do that piece by piece. So let's bring the 12 over here and the minus 10 over to make everything positive. That gives us 10 e to the minus 30k is equal to 3. Divide through by 10, and we get e to the minus 30k equals 3/10, or 0.3. Of course, we want to get to this k, so we're going to take a natural logarithm of both sides, and that will let us, as we'll review in a moment, bring down the exponent from the exponential here. So we'll have minus 30k is equal to ln of 3/10. If this is unfamiliar, don't worry, the next few videos are all about logarithms. But for those who do remember, this should be familiar territory. We've got minus 3k is ln 30, and so k is simply ln of 3/10 divided by negative 30. And with a quick piece of calculator work, we can actually find a value for that as approximately 0.0401. Or we could leave it in the exact terms we have here. And what that would give us is a very detailed formula, very precise formula for the function that we've described here. I'll just move this over for a second so we can squeeze in our t. There we go. 4.41 times t. So 15 minus 10 e to that will give us the inverted negative exponential decay graph here, going towards 15 as the horizontal asymptote, and with the scaling here that matches the data.